Hi, welcome to problem 10. We must find the zeta function of not an elliptic curve, but, well, we can say a singular elliptic curve where p divides to n. I may be wrong, but usually I think in splitting up the problem in smaller parts. So we have p distinct from 2, which means that p divides n, and that means in FQ the equation is y squared equals z to the third, and then when p equals 2, we can either have n odd or even, plus minus 1 is the same when we are in 2 to the rth, or 2 to the mth, and then n even, there should be 2, of course. Which is the same equation as above. So maybe we shouldn't treat that so differently. So let's look at this case first. And we're in the projective space. So 1, p divides n. So we have 0.0.1 and 0.1.1. The 0 and the point at infinity. It's z. If z is naught, then x must be naught as well. This was the point at infinity. Sorry. That's 2 points, and then we need to find those with non-vanishing. X and y. So we are in solutions in FQ start. It's a cyclic group with q minus n elements. Now, thinking here is that well, is that right? My idea was that t to the third point t squared parameterizes the solutions. But is this true? If y squared is a cube, So we have a generator here, and then one, two, three, four, five, six, 7, 8, 9, 8, 10. Should it be a power of 2 here? We should have 16 then. Or let's just have 8. 1, 2, 3, 4, 5, 6, 7, 8. So g to the 8th is unity. Now, which solutions do we have here? We have 1.1. This annoys me a bit. Then we also have to count how many distinct guys we have here. Maybe that will be easy. You can just as well say it's q to the rth that we are operating in. So what I basically wanted to say that if some of these guys, y squared, is a cube, must x itself then be a square? That's my question, basically. Oh, I think it's very simple. We have to go back to working with modulo numbers, modulo q to the rth. And then powers, that means just multiplying. So if 2n equals 3m, that means that q to the rth divides 3m minus 2n. Does that make me any wiser? What is it I want to prove? I want to prove, say, that 2 divides m. All right, either I'm out on a limb here, or I'm not thinking very clearly. That means it's time for a break. Well, I can just mull it over. Hi, I have a quarter of an hour before I need to get ready for tennis, but I thought I would just report on what I've been doing in respect to problem 10. I got the idea last time that the equation 2i equals 3x in Zn has the solutions 2i.3i where I runs through Zn. And that would give us the number of solutions to be exactly n, which here's q minus 1, which we needed over here. And then with the two solutions we know, the center and the point at infinity, that would give us a total of q plus 1, or nr being q to r plus 1, which would lead to the z function 1 divided by 1 minus qt times 1 minus t. So that was the idea. I didn't know about this hypothesis, so what I do in that situation is I make a lot of examples. I also made a Z5. Actually, I only made Z3, 4, and 5. What I noticed there was that here this guy is 1-to-1, 2i is 1-to-1, in Z4, 3i is 1-to-1. And the point is that when any one of these rows is 1-to-1, then we have exactly n solutions, because they can be parametrized by computing the first one and then going backwards. Where does 2 come from here? It comes from 2. Where does 0 come from? It comes from 0. So the only problem where this could fail is if both 3 and 2 and 3 divides n. So I tried with 6 and 12. And here we have the same phenomenon, or another phenomenon, by the way. Naught we get twice, and that's the only one that occurs in both rows. In set 12, it's 0 and 6 that occurs in both rows. And 0 occurs twice, like it does here, and 6 occurs twice, and here 0 occurs 3 times, as well as 0 and 6 does here. So we have x may be 0 or 3, y may be 0, 2, or 4, and all the 6 combinations work. So we have 6 solutions here, and the same guy here. We have 6 solutions with 0 and 6 solutions with 6. So, can we prove that these guys are distinct? Assume to the contrary that 3i equals 3j. 3i, no, 3j, and 2i equals 2j. In that case, we have two elements of Zn, which gives the same. Subtracting these equations, we get I equals j. So that means that the map is injective into the pairs. So we have at least n solutions, and it seems this way that we have at most n solutions. I haven't made the proof totally watertight. I need to find a way to formalize this argument. That was as far as I've come, working on the case that p divides n. The next one we need to work on is if p is 2 and n is odd. And of course we still work in FQ, where Q is some power of P. And this poor number here, let's call it M. Then the equation is and -1 is the same as +1. I could have written that up here, of course. -1 in FQ maps to +1. Because we have characteristic 2. And this actually equals x plus 1 squared. And if we disregard naught for the time being, then we can divide by it. Oh, that doesn't work. I believe here that we can let, now what can we do? We can set that equal to t, and then let t run through the multiplicative group of the field. Then we get a value for x, and then we are able to compute y. So I believe we have exactly q minus 1 solutions. And then plus the center, 0.0.1, and the point at infinity, we get q plus 1. I think this trick might be used here as well. This is the equation we want to solve. And how about subtracting 2x? And then setting t equal to y minus x. And then let t run through Zn. That gives us x values. And for each value of t and x, we get a y value. I believe I've solved it this way. So we don't need this hypothesis at all. That's just a nice result, but it's irrelevant, really. I like it, though. So what we need is to prove that in any case there is exactly qr plus 1 solutions, and that can be done with elementary algebra. In the case p divides n, we get this equation, and in case p is 2 and n is odd, we get this equation. I believe this solves the problem, so I was able to do it under time pressure. That the first time I've been able to do that, really. I had to stealth myself to be able to start, but that was it.